All right, so something that I want to kind of discuss or go over is kind of the history of chemistry, but mainly I'm just going to be going over some experiments that were used to create some core foundations within chemistry, some of the key logic that is used today. First up, we have the cathode ray experiment. So, cathode ray experiment was done in 1897 by J.J. Thomson. Essentially, this experiment discovered electrons, right? So, electrons are negatively charged particles found within atoms, and the setup of this experiment, the way he determined whether electrons exist or not, is he had this glass tube, and so this glass tube had little to no air in it, so it was very low pressure. The glass tube was coated with zinc sulfide, so zinc sulfide is a phosphorescent, and he also had two charged plates, anode which was positively charged and a cathode which was negatively charged. And he also had a battery. Battery is a broad term for this. He used a very high voltage electrical device to charge both of these plates, but for simple terms I just wrote battery. Ended up happening is that he discovered that when he applied electricity to both of these plates, both of these charged plates, a beam would form, not just any beam, a cathode ray, right? So that's where he gets his name from. Now, this ray or this beam wasn't a beam of light per se, it was a beam of high, fast moving electrons, right? Negatively charged particles. And they were moving from negative to positive. And the reason that he was even able to visualize this was due to the zinc sulfide, the phosphorescent coated within the glass tube. And he was also able to determine that, okay, this is something physical, right? This isn't just a beam of light. Whatever these particles are, they have a charge to them. So if encountered with a electrical field, or a magnetic field, they would distort, or the beam would distort a little bit, right? So he was able to prove that this is something physical with a charge to them, right? The next thing that he kind of discovered, or not kind of, the next thing that he did discover was the charge to mass ratio. And so the charge to mass ratio is exactly what it sounds like. It's literally the charge to mass ratio of an electron. Charge to mass ratio with an electron is big. It can mean the charge is either very large or the mass is very small, vice versa. If the charge to mass ratio is small, it means that the charge has a very little, or it means the electron has a very little charge compared to the mass, right? The biggest thing that you should take away from this is that he discovered electrons and the charge to mass ratio. So we have the oil drop experiment. Now, this was done by Robert Millikan in 1909. And essentially, this is something that he did in order to calculate the charge of an electron, right? The exact charge of an electron. And so what ended up happening is the setup consisted of a chamber. He had a chamber with an atomizer, which he sprayed oil droplets in. He had, again, similar to the previous experiment, he had two charged plates, positive and negative. He had ionizing radiation to kind of stimulate the whole thing. And then he had a telescope or viewing piece that he used to observe what was actually happening within the chamber. And something that he noticed was that he was able to adjust the voltage within the chamber to suspend the charged oil droplets in midair. He also noticed that any of the oil droplets inside of the chamber would actually pick up an electric charge, right? And so he was able to change the voltage so that they would hover, right? So if gravity is pulling the oil droplets down just naturally, and the electric field is pulling them up, he was able to adjust it so that they would hover. If they were hovering, that means both of those forces were equal, and then he could estimate, or he could come up with the exact charge of the oil droplet. This was also partly due to the fact that he knew the mass of the oil droplet and he knew the strength of the electric field. Next up, we have the plum pudding model. Now, this is going to be contradicted in the next experiment, but the plum pudding model was essentially an early adaptation or an early visual of what an atom was thought to look like. They thought atoms were positively charged spheres with these negatively charged electrons scattered throughout them, right? This was illustrated or theorized by J.J. Thomson in 1904. The only incorrect thing about this model is the fact that there's no nucleus. And so that was done in the next experiment, right? The gold foil experiment. Now, this one is actually pretty cool. I like this one, right? This is done by Ernest Rutherford in 1909. Essentially, this experiment consisted of a gold foil, a thin sheet of gold foil, and alpha particles. So alpha particles are made up of two neutrons and two protons, and it is a positively charged particle. And they are not big enough to necessarily shoot through, or they're big enough to shoot through electrons, not big enough per se, not necessarily bigger than an atom, but bigger than the electrons, of course. And so the theory was that he was going to shoot these alpha particles through the gold foil and that they were going to shoot right through. He obviously thought about the fact that there are electrons within them, so the alpha particles might get deflected by some of the electrons, which would explain the kind of uneven trajectory from these alpha particles on the other side. But he was able to see that, okay, these are going to shoot right through, right? Something didn't quite go as planned. He noticed that some of these alpha particles actually bounced back, right? This didn't make any sense, right? They were supposed to shoot right through the atom, supposed to shoot right through the electrons. The electrons aren't big enough to deflect them back, but they're big enough to kind of distort the trajectory, right? Ultimately, he concluded that atoms have a nucleus. So the nucleus within the atom is very dense. It's very mass heavy, or it's the heaviest. It takes up most of the mass of the atom, I should say. And that was what was actually deflecting the alpha particles in the first place. His theory still applied, or the logic still applied, where it's going to shoot right through the atom, and it might get deflected. It might get deflected by some of those electrons. But atoms in nature, or atoms realistically, are fairly empty, right? They're fairly empty spaces, the nucleus being the most dense part about them. And yes, they do have those, electrons within them, those negatively charged electrons, but most of the density comes from the nucleus. And so ultimately, that is what the gold foil experiment concluded. But yeah, anyways, I hope this was super easy to understand. If you feel like you need to touch up on anything, please do so. But other than that, this is the end of the video.